All right, so here is my little two different ways that you can think about it. This is the graph of x squared minus 2. And this is the graph of the square root of x. So the square root of x squared minus 2 is some combination of those two. Now we've done adding and subtracting functions, and we've done products and quotients of functions. This is neither of those. It's not just combining them that way. So it's combining them in a different way. But somehow, if you think about it, it's related to the square root of x, and it's related to x squared minus 2. Or you could think about it as this is the square root of x minus 2, and this is just x squared. I think the other way is probably will be a little bit more helpful to us, but it really, either way, makes sense the same, right? If I take the square root of x minus 2, which is this graph here, and I replace x with x squared, so I've taken two functions and I've mashed them together in a special way, which is what we're doing today, then I get this graph, which is the one that we're talking about. So if you zoom in, you can't see exactly what this is, but this is 1 and this is 2. So this is about 1.4 something, which is the square root of 2. Because below that, whoops, wrong one. Below that is where the parabola, the x squared minus 2, which is the radicand, the inside the square root of this function we're exploring. If it's negative, when I put that into the square root function, it doesn't work. So that's obviously an important, like the domain, in a sense, is an important part of thinking about what these functions are like, what they look like, what they act like, that sort of thing. Okay. And then if I think about, well, I'm putting x's into the square root, and usually I just put in x, like 1, 2, 3, 4, but now I'm putting in x squared. So they're getting bigger. Like as x increases, y is going to increase faster than just the square root function. So again, that's kind of why it obviously grows quite a bit quicker than the regular square root function, and it goes off. But it is still it would still kind of curve. It almost looks like it's going straight in the end. It's got a curve in the very beginning. Okay, so that is the composition of functions, in a sense, which is what we're doing today. It's when you take two functions and put one inside the other. Okay, so let's. So you could graph those. Hopefully, just the point of that little activity was just to think about kind of domain and then range, like what are the possible inputs, what would the output look like, that sort of thing. That's an important part of exploring these functions. Okay, so here we go. The other big thing, I mentioned this a few days ago about today, is notation. You got to make sure you get the notation right. There's a slightly new notation. You see it in part B there, and you need to know it just to be able to answer questions the right way, obviously. So we have two functions, a linear function and a quadratic function. We've added those in the past, which just gave us, if I added these, I would get another quadratic. If I multiplied them, I would get a cubic. So we've done different things with these functions, right? But now we're putting one inside the other. So what exactly does that look like? Well, think about what this function notation means. It means if this is f at x, wherever I see an x, I put this. What is this? It's x squared minus 5. So I'm going to start writing out f at x, which is 3 times x, but instead of x, I'm putting in x squared minus 5. And then the rest of f at x is plus 1. So I've put one function, subbed it in for x in the other function. And that right there is a composition of functions. So if I did f at 1, that would be 3 bracket bracket plus 1. I'd put 1 in everywhere that there's an x. Be careful of that. It's an easy mistake to make if there's multiple x's in a question, forgetting to put it in each one. Okay. So if I do it this way for just a number value, I do it the same way if it's a different expression. And then in this case, I can simplify this a little bit. So this is 3x squared minus 15 plus 1, which is 3x squared minus 14. So the part B here, we would read that f of, the first one, sorry, A is f of g. So the next one is g of f, or g circle f, or g o f, or there's all different kinds of words that they use for compositions. But we'll just say g circle f or g of f. So this is like g at f of x. So it's the other way around. Is it going to be the same as the first one? What do you think? I mean, you can start doing it, but just imagining how it's going to work subbing f into g instead of g into f, do you think it's going to work out the same? So I'm going to write down, I'm going to write down g of x, but instead of x, I'm going to put brackets. And then I'm going to put f of x in for those. Okay, expand and simplify. 3x plus 1 all squared is 9x squared plus 6x plus 1 minus 5. 9x squared plus 6x minus 4. Not the same. Any questions so far? So that's a matter of fact what composition of functions means. This is the last type of combination that we're going to look at. Putting one into the other. But we're going to explore something that's about it that's a little bit complex. But that's the basics. A little bit of notation, the circle notation, and a little bit of just what it means. And so now when we go back to that other, that first example, you can see how I either subbed in x squared minus 2 into the square root of x. I could think of it that way. Or I could think about I subbed x squared in to the square root of x minus 2. Both would give you the same end function, right? So we don't know where it came from, but it's a combination, a composition of those two functions. Okay. Evaluating, this part's pretty easy. So again, f at x is 3x plus 1. So 3 times x, but g at x is x squared minus 5. But it's not g at x, it's g at 1. So I'm going to do this. Squared minus 5. And in there, I'm going to put the 1. And then f at x is plus 1. So I subbed g at x into f at x, and I subbed 1 in for x in g of x. Okay, and then this is 3, so that's 1 minus 5, which is negative 4, which is negative 11. Or I think some of you are probably asking in your head, couldn't we have taken this function here? Because that is f at g of x, right? Couldn't I just do that? So what it's 3 times 1 squared minus 14. So 1 squared is 1 times 3 is 3 minus 14 is negative 11. Both are fine. If you've already calculated the simplified version, sure, like on a test or something, you could absolutely substrate into that, which would be that type. If you haven't, then maybe you do it this way. It's up to you, right? But you should be kind of thinking about how both of those are the same. Okay, why don't you try D on your own? Okay, so both these ways work. Again, I can go back to sort of the basics and start with the original two functions. And remember, one of them was x squared minus 5. But what am I subbing in for x? I'm subbing f in, and then in for x. In f, I'm subbing in 0. Or that's our simplified version, which was 9x squared plus 6x minus 4. So 0, 0. And in this case, this one's really easy. It works out to -4. But this one works out to 3 times 0 is 0 plus 1 is 1. Squared is 1. So 1 minus 5 is -4. So obviously they work out the same. It always has to. But both ways work. Again, neither way is better than the other. It's just a matter of a preference or circumstance. Any questions about that? Fairly straightforward, I think. Once in a while, people get it backwards. G circle F, they make it F circle G, and we saw that it's not the same. So that's what I mean about notation. Like, you got to figure out which one's right. Okay. Here's the part that can be a little bit trickier. Sometimes it's pretty straightforward. Once in a while, it can be quite confusing. We're going to determine the domain of all of these and the range of some of them. And if you're writing down that definition, I'm going to explain it in a moment. Or we'll do F and G first. We'll do A and B first. So again, great. You can go ahead and do that. You don't have to wait for me. Great review. The domain and the range. The domain and the range. Okay, I hope you got that. Oops. So just this plain old square root function, greater than or equal to 0. y is greater than or equal to 0. And b has a reflection. So instead of going up, it goes down. It can, x is an element of the real numbers for the exponential function. And so it's less than 4. Alex?
Wouldn't b's range depend on 1 from x? Or is that those three wouldn't be cubic functions?
Sorry, say that again?
If x is 3, wouldn't it be a cubic function?
X changes.
Or wouldn't it be a cubic function if it was?
Then if we set x equal to 3 permanently, there's no x left in the question. It wouldn't be a function. It would just be evaluated. X is what we're subbing in for, right? And x is what changes. And then we're thinking about how does the y change as x changes. So it's exponential function. Okay, so here we go. Put your pencil down and just watch for a minute, okay? This is a thinking exercise, and you really have to follow. And you might not get it the first time, but part of what you want to do today is really work through it and figure this stuff out. So f of g, let me write this down. That means the square root of negative 2 to the x plus 4, right? Yeah. So like we did in that first exercise, think about that function. You know that the square root, what you put into the square root, the radicand has to be greater than 0. Like, you know that. So now you're starting to think, well, what makes negative 2 to the x plus 4 greater than 0? In other words, when is that greater than 0? Right? Like, that's what you have to think about. Here's the tricky part. This evaluating to anything, but in this case something greater than 0, is like when the range of this function, which is g, when that range is greater than 0. Okay? Does that make sense? So when the range, and what was the range? The range is less than 4. So sometimes it's going to be bigger than 0, and sometimes it's going to be smaller than 0. The output of this function. When it's positive, our new composition function will work. Does that make sense? Is that easy? So then what's the domain of this function? Well, the domain of this function is actually the domain of this function when it gives an output that is positive, 0 or greater. So it's not just like greater than or equal to 0. Like, it's not, what you're going to find is the domain of a composition of functions is not equal to the domain of one or the other of the functions. That's not how it works. Whereas with other combining functions in other ways, adding, subtracting, multiplying, dividing, the domain was just the overlap of the other domains. Not the case in composition. So let me see if I can, I'm going to do a little graphic, and then you can just kind of think about it. Where can I do it? I'll try to do it right here. And look at this graphic later after you're thinking about this and really try to make it click. Because if it clicks, then I think this won't be so bad. Okay, so here is the domain of G. That's what's going into F, I believe, in this example, right? Yeah, because it's F of G. Yeah. Okay. So the domain of G goes to the range of G. Right? That's what it means to have a function. Something you have your input, which is your domain, and your output is your range. And so this is the, inside this circle is the set of all things that are in the domain of G, whatever they are. Now here's the tricky part. The range of G will overlap partially or maybe fully, depends on the example, with the domain of F. And in this case, remember the domain of F, which was a square root function, has to be anything greater than or equal to 0. So sometimes the output of G will overlap with the input of F. Do you agree? Do you understand that? Able to follow that? Again, if you're not able to follow that, that's fine, but go back and think about it. Okay? And then this part's not as interesting to us, but this would be the range of f. We're not going to worry too much about that right now. Okay? So I've got this part, which I'll color in kind of red, and I've got this part which I'll color in green. And what I'm going to try to do to visualize this is I'm going to pretend what those parts are back in this domain. So the red part in the domain maps to the red part in the range. Do you understand that? And the red part in the range does not fit in the domain of f. Do you understand that? So that's not part of our domain of f of g. Because it's fine for g, but the output gives me something, in this case, that's negative and doesn't work. So what about the green part? Well, the green part is in the domain of g, and its output is positive, so that works for f. So it's good. But the input of the entire function, so the domain of f of g is just that green part. It's the x values that we plug into g whose output fits f. It's very tricky, and it's something you need to think about a few times. The domain of f circled g is the set of values in the domain of g for which the output of g is in the domain of f. The textbook has this definition and has a graphic that's similar to the one that I did, but not, I think, not quite as good. So if you need to look at that graphic that I have online yesterday and look at the color coding, it might help when I put it up later, okay? Okay, so let's see if we can finish this. Oh, people are writing that down. Got that okay? It's not a definition that's simple or like concise. Like there's no way of simplifying that definition any more than sort of what we've done already. Okay, so it really does take some time to think about. So what is the domain? We're only going to worry about domain for now. Once in a while, you might have to find the range. So that's something else that you want to think about. But what is the domain for f circle g? In other words, when the output of g is positive, when will that occur? Do you have a question?
No, would it be greater than 0 and less than 2?
Why do you say that?
Well, because like inside the square root, wouldn't it have to be a positive?
Mm-hmm.
And the only times that like something that like 2 to something would be a number with still with a negative out in front.
Good.
Like and adding 4, and it would still be positive. When 2 is brought to the exponent 0 or 1.
Okay. I understand what you're saying. You're on the right track. There's one thing that Zoe said that I think is something like that you have to somehow force your brain to get around. So when you said greater than 0, you're right that the radicand has to be greater than 0. But what values of x will make it greater than 0? So in other words, what happens if I put a negative value in for x?
It would be a fraction, so it can be anything less than 2.
Okay, good. So if I put, and this may be part of what you do, is you think about possible values. What happens if I do this? What happens if I do this? That could be a tactic that you use. Again, we're not going to do very much of this, right? Our test is tomorrow. So if I put a negative value in for x, what does that do? It makes the 2 the reciprocal. So if I put in negative 1, it's a half. So it's negative a half, which is smaller than 4. So when I add 4, it's going to be positive. And any negative value of x will make this negative part very small, smaller than 4. So I'll be adding something negative that's small to 4. And I'll have a positive value. So any negative x is fine. Is 0 fine? Yeah, 0 is fine because that makes this 1. So it's still negative. It'd be negative 1 plus 4 is 3, right? And what about 1? And then what about 2? Well, 2 squared is 4. That's negative 4 plus 4 is 0. That will work. But as soon as I go over 2, that will no longer work. But before you write any of this down, this is our graph, something like that, right? It's flipped and it's shifted. It's an exponential function. It's shifted up 4. When does the output become negative? At 2 along the x-axis. So that's our domain, right? The range is greater than 0, but we have to follow that back to what made the range of G positive. Okay, I'm going to stop talking because I think you need to take some time to think about it. So x is an element of the real numbers such that x has to be less than 2. Now, there's, in some cases, an easier way of doing it. In fact, in this case, it's maybe not really easier because it requires a couple of things that we've not talked about in this course, so it's not things that we know to be true facts. But I'm going to show you something, and in some cases, it will absolutely work. Is I know if it's the square root of negative 2 to the x plus 4, then what I know is negative 2 to the x plus 4 has to be greater than 0. So in this case, I'm not even thinking about the domain and the range of either individual functions. I'm just thinking about the final function and what has to be true. But this is not an inequality that we've solved, and it's not an inequality that, to be quite honest, you have the facts of how you would solve it, right? Because we never talked about squaring or square rooting both sides of an inequality. Does that preserve the inequality? Or does that, remember, sometimes you flip and sometimes you don't. Some operations flip, some operations don't. We've not talked about that. So this would be solved this way. And then divide both sides by a negative. So that's 2 to the x less than 4, which is 2 to the x less than 2 squared. And then therefore you could do x is less than 2. Like, it does kind of work the way in this case, the way your intuition would have, but I don't suggest doing that with new things, new inequalities you've never seen before. Tricky stuff for the last lesson ever, but it's a tricky course, so there you go. Okay, let's try to do this one. This one's a little bit easier. Because it's the output of F that's going into G, right? It's the output of F that's going into G. But G will take anything. G has a domain where X is the element of the real numbers. So where does the output of F, which is the range of F, where does it overlap with the domain? Well, everywhere that the range exists. But again, I don't use the range. I have to go back to the domain of F and think about which values gave me the range. Last time, what I mean by this is, I think about the range of this and which ones overlap with the domain of this. But then I have to, that's not the domain. I have to follow it back to the original to get my domain of the new function, right? That's what I mean by that. Okay, so, whoops. So in this case, does anybody know what it is? Yeah. Greater than or equal to, right? Yeah. So x is an element of the real numbers such that x is greater than or equal to 0. And the range of that one would be something that you could certainly determine. How would you do that? you'd plug 0 in, see what you get, and then I believe it will go up from there, right? So it would be everything from that value and greater. But see how there's no like rule, because every function is different. And all we've done is looked at a log and a square root. Or sorry, not a log and a square root, exponential and a square root. What if it was a log and a square root? What if it was a sine curve and an exponential function, or a sine curve and a cubic? Like, it becomes tricky. Well, those ones, their domains are a little bit simpler, so it might not be so bad. Okay, a couple of, these are easy. So here's what I want you to do. I'm going to let you try this on your own. See how it gives you the composition of the two functions, f circle g? You have to decompose it into f and g. So what could f at x possibly be, and what could g at x possibly be? So see if you can come up with two combinations on your own. Go. Okay, who's got one? Roman?
Where f of x is equal to the absolute value of x plus 1, and g of x is equal to x to the power 3.
Nice. Simple one, right? Come up with a different one. If that's the one you had, come up with another one. Who's got another one? Yeah, that's fine. A lot of them are going to be easy. Nice. See how, that's good. That's great. See how like you can do it either way? Anybody have a different one?
F of x could be x, and then g of x could be the absolute value of x cubed plus 3.
So, yeah. So one of them is kind of the original function, but she's right. Now that would not be allowed on a test. You'd have to break it up more, but you're absolutely right. Yeah, very good. Any others? Or vice versa. You can flip that around the other way, right? It would still work. Okay, let's try B. So I asked you to come up with two, so try to come up with two, but if you come up with a third one, it's even better. Who's got one? Bishoy?
F of x would be x plus 3, and then we go into x squared minus 5.
So this one is F into G, right? So very good, yeah. Because if you did it the other way, that wouldn't work. No, I think you did it the right way. Yeah. Yeah, you're good. Yeah. Another one, Roman?
Something like, so you have so we could have like, for example, g is like x plus 5, and then f is x squared minus 10 or something.
G is X
Plus 5.
plus 5
And then f of x is squared minus 10.
x.
Oh, sorry, it would be x plus 3 squared minus 10.
Oh, okay, I see what you're saying. X plus 3 squared minus 10. Yep, that's right. So if you think about that one, yes, it'll work. Anybody have another one? No other ones? What about x plus 3 all squared and x minus 5? Another one. Okay. C and D. Go ahead, try a couple of different ones. Who's got an idea for C? Hunter?
2 to the power of x minus 1, and then 5x.
Nice. 2 to the x minus 1, and then G would be 5x. Good. Anybody have something different? Okay.
2 to the 5x and then 1 to the x minus 1.
1 to the x minus 1. Yeah, you're on the right track. Hold on. What did you say for the first part?
2 to the 5x.
I think if I put 2 to the 5x here, that's g at x, and I sub that in to x minus 1, which is, I think, kind of along the lines of what you were trying to say. That won't work very good. Anybody have anything for D? Hunter, go for it.
Log x, and then bracket 2x plus 3 all squared.
Log of x for f at x.
For f and x, and then g and x will be 2x plus 2 all squared.
2x plus 2 all squared. Really nice. To the negative 2. Because it's negative?
So yeah.
I thought you were making a mistake, but you got it. That's right, because you can take the negative 2 of the exponent out to the front. Nicely done. Anybody have another one? There's an easy one, right? I could go negative 2 log of x and 2x plus 2. So kind of similar, but not quite as nice as Hunter's. Anybody have another one? Anybody? What about this? Negative 2 log of 2x and then x plus 1. That'll work. There's all kinds of different combinations. What about negative 2x and then log of 2x plus 2? Lots of possibilities. Okay.